Okay, so I'm going to work through this example that we didn't have time to do in class about a baton twirler that throws a baton into the air and what happens with the baton. And before I start working on it, I want to really strongly recommend that you take the time to try to work this problem out on your own before you watch the solution video, because I think it's really a helpful problem for thinking about what assumptions you can make and not identifying what's happening in a problem. Okay. So I'll give you a moment to pause the video. If you haven't tried it, give it a try, and then I'll do that kind of at each part too before we start. Okay, so I'm going to start by drawing a picture. So I've got a person who is holding a baton that's twirling like this, and it's got two flaming masses at the end. This problem was inspired by a physics major baton twirler who was in my class last semester. And when this baton leaves the twirler's hands, it's rotating at omega equals 2 revolutions per second. And then it reaches a height of 5 meters before heading back to the ground before he safely catches it. Okay? So the first question is, what is omega at the top? Okay? All right. So to think about the change in rotational motion of this baton, we want to think about whether or not gravity exerts a torque on the baton. So let's draw the baton by itself over here. It's rotating at some speed, and then we've got the force of gravity that's acting at the center of mass. Okay, and so note, because gravity is acting at the center of mass, there is no torque, okay, from gravity on the baton. And so that means that it's actually not changing the angular momentum. And so we can also think about, we can set our origin as, at this position, say, and then we can think about what happens as the baton moves upward, right? It's still rotating, okay? Gravity's still acting at the center of mass. Here now, if this was our origin, our R is here, okay? And then R cross G is 0. Those are parallel to each other, so that's another way of thinking about that the torque is still 0, even as the baton moves up and down. Okay, so, and what that means is that omega does not change, right? So omega equals 2 revolutions per second at the top. Okay, so now let's pause for a minute. You can read part B, and then we'll talk about how to do it. And I'm going to give you a second to pause the video if you haven't yet looked at it. Okay, so for part B, we want to know what speed must the twirler toss the baton to achieve the planned height. Now here, okay, we only need to think about the linear motion only, and so this is just a kinematics problem, okay? So this maybe looks scary or hard, but this is just kinematics, and you know how to solve a kinematics problem, right? And so the question is, what is the, no, V naught is not 0. V naught in order for y final to be 5 meters. Okay, so y equals y naught plus v naught t plus 1/2 a t squared. We could use this equation, but we don't have time. Like, we don't have a value for time. So instead, it makes more sense to use this equation, this kinematic equation. Okay. So our v naught is, we don't know. Our v final is 0. Our a y is -g. And our delta y is 5 meters. So v naught squared is 2 times 5 times 9.8 meters squared per second squared, and our v naught is square root of this, which is 14 meters per second. Okay, so that's our part B. Now let's go scroll back up and read part C. So part C is, what is the total angular momentum with respect to the twirler's feet at the moment it leaves his hand and at the top of its flight? Okay, and it's asking you to assume that that the baton is thrown from a position straight above the twirler's outstretched arm, kind of like I drew it in the picture. What's that, the length of L arm? And I've also given you some information here about the baton and its mass and the mass of the other things. Okay. All right. So I'm going to draw the picture again here. And then I'm going to give you a moment to pause it and try to calculate this yourself. Okay. So this is our picture initially. This is our final picture. Okay. So we are going to have a origin that looks like this. That's at this point between their feet. And that means that this our initial, we're going to write that as a vector. This is the height. And I told you that the distance from their center of mass was L arm. Okay. That's h is the height of the baton, which I think I forgot to give you in the problem, but we're just going to call that h throwing. Okay, so we can write this as a vector. So the height, the position of the baton at the start is L arm I hat plus, I should make this an L, lowercase l, even though I told you capital L, just so we don't confuse it with momentum, plus h throw j hat. Okay, that's our R. And then our total angular momentum is going to be our L center of mass plus our L of spinning about the center of mass. So that's R cross P plus I omega. Let's find the spinning one first. So L spin is I omega. Let's find the I of this moment of inertia of the whole thing, which is the I of the baton plus 2 times the I of those masses. So the I of the baton, we're going to use this here. Okay. So that means that the baton is 1/12 ml squared, and then 2 mr squared for the individual masses. The individual masses is the mass of the whole thing over 12, and that R is L baton over 2. So we've got 1/12 ml squared, m baton squared, plus 2 ml baton squared over 12 times 2 squared. So that gives us the total I is 1/12 ml baton squared plus 1/24 ml baton squared, which is 3/24, which is 1/8 ml baton squared. Right, and then our omega is 2 revolutions per second, which is 2 pi radians per revolution, so that's 4 pi radians per second. So our L spin then is 1/8 ml baton squared times 4 pi. And we want to think about the direction of this. So to identify the direction, we need to decide whether our baton is rotating counterclockwise or clockwise. Since I didn't tell you, we'll just state and make an assumption. So we're going to say assume counterclockwise rotation. Okay. And then the way I have defined these axes, I've got X, Y, Z like this, right? So Z is toward the person out of the page. And so that L spin is in that direction. So it's it's pi over 2 ml baton squared k hat. All right. Now we want to find L of the center of mass. And that's going to be R cross P center of mass. So we found our initial R at the beginning, which was L arm I hat plus H baton, or H throw, we called it J hat. And then the initial V is V naught J hat, heading upward, right? So R naught cross P is R P sine theta. P is M total V, and our M total is M plus 2M over 12, so 7/6 M. Okay, let's look at the angle here. So we've got H, let's not write this at the junction between pages, so H, L, V is pointed in this direction, so this is our R, this is our V. We can draw our V down here, so this is our theta. So theta is tan inverse of L arm over H throw. Okay. And then the direction here of this momentum is going to be in a direction that comes out of the page also, right? L is out of page, so also positive k hat direction. So the total angular momentum initially is square root of L squared, L arm squared plus H throw squared times M 76M times V naught times sine theta, which is L over square root of L arm squared plus H arm squared. So we've just got L V naught M. Okay. That's our center of mass one. So our total L is this plus our spin angular momentum. So we've got 7 L V naught M over 6 plus pi over 2 M L Baton squared. Okay. So that's our total angular momentum initially. Then what about at the end? So at the end, at the top, L is R cross P plus L spin. The spin angular momentum hasn't changed because there's no torque about the center of mass. P final is 0 because at the top of the trajectory it's not spinning. And so this final angular momentum is actually just the spin angular momentum at the top of the trajectory. So that's just pi over 2 ML Baton squared. K hat. Okay, and so this is confusing, right? Because now we're saying the angular momentum changed, but we said earlier that there was not a torque. And remember that whether or not there's a torque depends on your axis, okay? So if you're puzzled by that, but think you might can figure it out, pause the video now, see if you can go back to what we thought about at the beginning and what we're doing now and figure out where the discrepancy is. And if you're still stuck, or if you want to check your answer, you can do that now. Okay, so at the beginning, right here, we chose our origin at the position where the person was holding the baton at the beginning. And about that point, there was no torque because gravity was pointed just along the direction of motion. And so that meant that there was no torque around the center of mass. But then we've got a new frame down below here, where now our origin is here at the person's feet, okay? Now, in this frame, in this origin, this is our R, and this is our force of gravity. So those do have a torque, and they have a torque that's pointed into the page. Torque pointed into page, okay? And so what that tells us is our torque should decrease the angular momentum in the z direction, in the k hat direction, because it's pointed in the negative k hat direction. And indeed, that's what we found, right? So we found that our initial angular momentum here was at the beginning when throwing was this. And then our final angular momentum here was at top, okay? So the gravity is exerting a torque that is in the negative z hat direction, negative k hat direction, and is decreasing the angular momentum as we expected. All right, that's the end of that problem.